This is the second time I'm doing this video because the first time I'd recorded over it. Hi there. I'm doing this one again. This is the second capacitor example in which we take a look at how we can think about capacitors conceptually if we kind of do some stuff to them. So let's do this. Let's say we've got a parallel plate capacitor, boing boing, and we charge it with a voltage source. So it's got some voltage going across this, whatever it is. This side is the classic positive, this side is the classic negative. Okay, and it's separated with some distance d, and like I said, it had some voltage across it. Now, we remove it from the voltage source. And when we do this with a capacitor, because we've actually placed charges here, there's still a voltage across it. And this sucker is still charged, which is actually very dangerous for some electronics. If you're fiddling inside an old tube TV, like a CRTV, the big heavy ones, not your like thin flat screens you've got nowadays, the capacitors in there, in order to get those to work properly, were actually pretty large, and they stayed charged for a very long time. So if you're opening one of them up in your garage, be careful. Make sure you discharge that capacitor because you can pretty easily kill yourself with it. So be careful. Now, let's say we've got this capacitor here, right? But then what we do is after we've unhooked it, it's still charged, we pull the plates apart so that they are now twice as far apart as before. They were at a distance d before, now they're at a distance 2d. They have the same amount of charge on it because the charges couldn't go anywhere. We're insulated or whatnot. So same amount of charge, but the distance changed, and we've got a new voltage at the end of this. Okay. How will the stored energy of this capacitor change when we pull them apart? That's what we're looking for. How will this energy here change? Well, let's go to two equations real quick. The first we're going to look at is the actual capacitance of this capacitor. When we pull them apart, we change the physical geometry of the system. And for the capacitor, we know this is kappa epsilon naught A over D. Now, kappa is the dielectric, so it's constant here. Epsilon naught's a constant, and we haven't changed the area, so that's the same. What we have done is we've increased this distance, and since that's in the denominator, it's actually going to lower our value of the capacitance because we're dividing by a larger number. Now, if we've lowered this capacitance here, if we go ahead and use the equation that the stored energy in a capacitor, is 1/2 Q squared over C, well, we see we're lucky enough here that the charge stored on the capacitor is a constant, so we don't worry about Q. The charges couldn't go anywhere, but we did decrease this capacitance here. Well, once again, if we've decreased something in the denominator, we're going to increase our actual value of the stored potential energy here. Okay? Now, that's how the energy changed in this problem. Something that's kind of a little weird thinking about, though, is, what if I thought about this in terms of the voltage? Well, the voltage is actually going to change as well. If you remember, voltage is equal to the charge over the capacitance. It's actually how we were able to write out this equation. Since that charge can't leave and it's a constant, but we know the capacitance has to go down, we know this voltage here is actually going up in this problem. So there's a few other ways that you could write this out, and we would see that the voltage going up would cause the same thing. If we wanted to rewrite that, we know there's an equation. We can say 1/2 Q times V would also be equivalent if Q is a constant but voltage goes up. We see that the stored potential energy in this capacitor is going to go up as well. So that's what's going to happen whenever we pull this apart. And it makes sense because these plates are attracted to each other. They want to be. As we pull them apart, we've put work into this system. And if we're putting work into the system, we're storing energy there, moving the plates apart. They want to come back together if possible. And that's how we see this potential energy increases. So with that, this is finished. Not too bad. We've got one more capacitor example we're going to look at, and then we are going to start moving into electric circuits. So until next time, adios. Take it easy.